Hi, good evening, all. This is Vishal Singhal from CellStrat. I am co-founder and AI evangelist with the company. Today we have Mr. Natarajan Lalgudi. He's AI researcher with us in CellStrat AI Lab. He'll be taking us through comparison of boosting models in machine learning. Uh, so I suggest if you have any questions coming to your mind, please let them keep them coming, and we will answer them towards all of them towards the end of the webinar, unless it is slide critical. If it is related to the slide being discussed, then I will ask Mr. Rajan to respond to the same. Else we will be answering all of them towards the end. So this session is being recorded, so you will be able to see its recording in 2 to 3 days time on our CellStrat YouTube channel. I'll share the link while the seminar is on, webinar is on. I'm sorry. Uh, and yeah, so I'll just hand over the presentation to Rajan.
Yeah, hi, good evening.
So Rajan, go ahead, share your screen. I'm going on mute.
Yeah, hi, good evening. First of all, can I get a quick confirmation if I'm loud and clear to everyone?
Yes, you are. Go ahead.
Okay, all right, thank you. Thank you. So, welcome everyone to this presentation on boosting models. And I just like to first talk you through what is the intuition behind boosting. So, very often in day-to-day life, we hear conversations. For example, we just had elections, right, in a state. So, if somebody says that if so and so person stands on behalf of the party, then the chances of that party winning in that overall election itself will be so much. Versus if the person does not stand. In closer home, we have games like cricket. So there will be lots of rules of thumb which say that if Virat Kohli scores a century, especially in the second innings, the chances of India winning are 9 out of 10 or 9.5 out of 10. So very often you have these rules of thumb. In a data science sense, you can call them weak models, especially decision stumps or decision tree with depth of 1, just a stump, which is nothing but a simple crosstab, is a rule of thumb. And you have plenty of these rules of thumbs floating around, right? But the whole intuition behind boosting is that in the late 1990s, a couple of data scientists in AT&T labs called Fruint and Chapire discovered this algorithm called Adaboost. They invented this algorithm called Adaboost or adaptive boosting, which converts weak learners into strong learners by simply overemphasizing or overweighting the wrongly classified samples. The default base estimator is a decision tree stump. And in the words of none other than Leo Bremen, the inventor of random forest, which was the big algorithm before that in the early 90s, he calls boosting the best off the shelf classifier in the world. So moving on, so a lot of this may sound to many of you who are familiar with algorithms like random forest that it's what is the difference between this and bagging? It seems very similar. So bagging is a set of creating multiple classifiers or trees which are fairly homogeneous or similar to each other, wherein you're randomly sampling parts of the data as well as randomly sampling certain features. And they're fairly homogeneous in nature. So the overall voting that you gain from bagging is like gaining wisdom from the crowd, right? Like how we have in Kaun Banega Crorepati, where the audience votes in the end when somebody needs their help in answering a question or in elections. Because boosting is something far more radically different than that. Boosting is like wisdom from a bunch of fools. And just to illustrate how this one can relate to this a little better, it's something like this. So in electoral democracy, everybody is casting their vote, but here there are people who are completely clueless about what this elephant looks like. But if you take all these weak learners and you assemble them together, you can pretty much grasp the entire picture of the elephant. So here is a bit of a starter on how the intuition works as far as boosting is concerned. So what Adaboost typically does is it uh, it takes the initial classifier and it starts identifying those elements. Like if in the graph, if you see in the left hand side of the slide, if you see which have been weakly or wrongly classified, and in the next iteration they get upweighted. So the next round and the subsequent rounds, these particular samples get upweighted. So they're actually there's no reward in the next rounds for those samples which are correctly classified, and so on and so forth. And ultimately, all the weights and the classifiers are combined together. And when the training error doesn't reduce any further, that's when the set of iterations are stopped. And ultimately, all the classifiers are voted together using the weights of the classifiers themselves to get the final prediction for the ground truth label. I'll talk about this a little bit more in detail. So this is not going to be the only slide on this. So this is again another intuition in terms of how you have the sequence of boosted trees to ultimately arrive at your classifier. So alpha in this case will be your weight updation. So this is the Adaboost algorithm, and the Adaboost algorithm is nothing but uh, taking a set of classifiers which can potentially classify the data set that you are involved in, and identifying the data set first, the classifier first, which has the lowest entropy, which has the highest impurity, and taking that as your base learner. So a decision stump of your weakest classifier will be your base learner for your first round, and uh, basically you will then have alpha, which is the amount of say or the weightage that the first tree will get, and then again there'll be an alpha for the second tree, and so on and so forth. So alpha is nothing but half into log of 1 minus the total error upon the total error, and then you update this for the entire uh, sequence of trees. Let me explain this with the help of an actual example, which will make life easier for all of you. So let's say we have a data set, yeah, which has 7 records, and these 7 records can be predicted with the help of 3 features or 3 classifiers, say F1, F2, and F3. Now the initial weights for all the records is 1 by 7 or 1 by n, right? First step is to identify the base learner. So amongst F1, F2, and F3, the feature with the least entropy, you can also use Gini if you want, or the highest impurity becomes the base learner, the weakest classifier. So let's say in this case it was F1, all right? Then the next step, you classify the dataset using the base learner. So supposing F1 misclassifies only record 3 wrongly out of the 7 records, just for the sake of the example. Yeah. So now the total error of the classifier in the first round becomes 1 by 7. So when 1 by 7 is the total error, what is the performance say that this classifier has in the overall scheme of things? Now, ultimately, the way bagging works like a democracy, where everybody sits and votes at the end, and each of your trees in your random forest gets an equal vote. In the case of boosting, each of the trees or each of the boosting rounds get a vote. The vote is in proportion to something which is called a performance say or alpha, which we saw in the previous iteration or the previous chart where the entire mathematical representation has been drawn. So alpha is nothing but half into log to the base e of 1 minus total error, or epsilon t if you want to call it, divided by epsilon t. So the performance say of the first learner will be half of log of base of 1 minus 1 by 7 divided by 1 by 7. This will be 0.896. So now what we will do is, now you have your performance say of this base learner, which is the weightage the learner will have when it finally comes to the voting table for each and every record. Now the second step is we have to update the weights at the end of the first round. Like I said, the misclassified samples will get overweighted. So how they will get overweighted is e to the power of the performance say will be the weight given to the misclassified samples, and e to the power of minus performance say will be the weight given to the correctly classified samples. So at the end of this, your misclassified samples will have a higher weight. So at the end of this, let's say your misclassified sample will have a weight of 0.347, and each of your correctly classified 6 samples will have a weight of 0.05. Now, when you add up all these recomputed weights, the total of these weights may or may not add up to 1. So the next step is to normalize these weights to simply ensure that all the weights add up to a sum of 1. So you just recalibrate them to ensure that the total of those weights is equal to 1. So now you have your recomputed weights, you have your first tree done, and you have your classification or prediction done from your first tree, and you also have your performance C of the first tree when it eventually comes to the voting table. So now we have to look at the second tree. And what we do at this stage is we actually just wipe out the entire data set. There is another method which is a little complicated in terms of weighting the Gini coefficients and so on. But a simpler way is to just wipe out the data set and construct the data set all over again using the records for the second tree and so on and so forth. So for the second tree, what happens is we basically calculate the cumulative distribution function of all the updated weights. So you have 0.07 in the first for the first record, then you have 0.14 at the end of the second, and then you have 0.65 at the end of the third, because your third classifier, your third record was misclassified, if you remember, and so on. And ultimately, the end of the cumulative distribution function will obviously be 1.0. The next step is that the algorithm selects a random decimal between 0 and 1. The value of the CDF weights of the weights closest to that value will indicate whether the record. So if let's say the number selected is 0.62, that will be closest to the third label. So the third record will then get selected in the data set. In this way, we will constantly select a random decimal and populate the entire data set again using the random number and using the records from the original data set. So certain records can actually occur more. So in this case, your misclassified one, because the weightage was higher, the probability of that occurring in a random selection between 0 and 1 will therefore be that much higher. So the chance that it may occur multiple times in your second state data set can actually be that much more. Yeah, which is where the entire philosophy of upweighting the misclassified samples is also coming into play. We then repeat all the steps which we did earlier. We calculate the total error, the performance say, and the updated weights till such time that there is no further reduction in the training error. Finally, when you have all your boosting trees and each of them has a performance say, how you calculate the classifier for each individual record label, you basically take the performance say of the learner, multiply it by the classified label, and build in a sign of 1 or -1 for right or wrong classification summed up across learners. So let's say if the first one is 0.896 and it is correctly classified. So the first that particular record will get 0.896 into 1. The second one is wrongly classified, and the performance of the second tree is the 0.634. It will be 0.896 minus 0.634 minus whatever. So if at the end of it, the sum of this weighted sum of the performance say into the classification 1 or -1, depending on whether it's rightly or wrongly classified, the sum is positive, then we can classify the ground truth label as the correct value. As otherwise, you classify it as the wrong ground truth label. So the ultimate classifier is correctly classified or wrongly classified, depending on whether the total sum, weighted sum, is positive or negative. Is this clear so far? Are there any questions here?
None so far. Go ahead.
All right. So just a quick wrap on Adaboost or adaptive boosting. It works well on simple and complex recognition problems. In fact, one of the very important face detection algorithms, which has been in place since the era of Y2K, which is the Violet-Jones algorithm, actually uses variation of Adaboost to convert weak classifiers into strong classifiers. And it's a very easy algorithm to tune. The space overfitting is a little slower. Of course, the disadvantage is that it is hugely susceptible to outliers and noise. So the beauty of Adaboost is it simply upweights the wrongly classified samples, and there is obviously a merit for correct classification. So if the tree classifies more samples correctly, it will have a greater weight when it comes to sit in the end to vote. Moving on to the next school of classifications, you have adaptive gradient boosting, and the other is you have gradient boosting decision trees, wherein we will now talk about 4 different types of algorithms. So the first gradient boosting decision tree algorithm is the gradient boosting machines. So it works sequentially, and each one corrects the predecessor. However, gradient boosting basically tries to fit the new predictor to the residual errors made by the previous predictor. So the first predictor, the first tree is fit on the training data. Once you get the residuals from there, the subsequent trees are all fitted on the residuals. So the entire objective is to constantly keep minimizing the residuals. Gradient boosting, therefore, is also very greedy algorithm in that sense. So adaptive boosting actually takes this whole philosophy of weak learners and converts them into strong learners. But gradient boosting's simple brief is to keep minimizing the loss function, iteration to iteration, iteration to iteration, using the gradient descent philosophy of the gradient descent algorithm. So again, the math side of GBM, so you basically fit a base learner, you generate predictions, you generate the loss function, and at each point you take a partial differential of the loss function with respect to the function, and you calculate the gradients, and then you fit a decision tree to all the negative gradients. And the equation obviously is f is equal to f plus alpha into h, where alpha is the learning rate. You typically have the Gaussian loss function as the default loss function in the GBM. So GBM therefore performs the traditional vanilla gradient boosting machine performs simple gradient fitting by penalizing larger deviations. It may or may not be therefore totally robust to outliers, which is why there is an option for selecting different loss functions depending on the kind of noise you have in the data and the kind of distribution tails that you're dealing with. So your GBM is nothing but your mean square error or your L2, which is half into y minus y hat whole square. But then you have your Laplace, which is your mean average error, or your L1, which is modulus of y minus f. You also have something called Huber loss, which is a combination of Laplace and Gaussian, and uses a hyperparameter called delta. So when delta kind of tends to 0, it's the mean absolute error, or L1, and when delta tends to infinity or larger, it is similar to your mean square error. Yeah, so the only disadvantage with Huber is that you need to keep constantly tuning that hyperparameter delta. You also have quantile loss, which, as the name clearly suggests, you keep predicting your data set on quantiles instead of predicting the whole data set, and you average them out. So this is just a visual representation of the residuals that you encounter from iteration to iteration in the gradient boosting model. So gradient boosting, unlike Adaboost, is therefore a very greedy algorithm. You know, all the gradient boosting algorithms that we will encounter today, and some of you would have already encountered them in your data science experiences, are very greedy algorithms. So regularization is a huge issue. How it can be handled is the traditional ways. You do bagging fractions or bootstrapping. You can also subsample or give fractions in terms of the percentage of features that you take prior to the construction of each tree. And then there is shrinkage in terms of the learning rate, which you can clearly control, so that the process of gradient descent is therefore not hastened too much or not slowed too much, depending on the nature of the iteration that you're building in terms of the number of trees you're taking. If you're taking more trees, obviously you need to have a lesser learning rate. If you take less trees, you could have a slightly higher learning rate. And there's also in gradient boosting the trade-off between learning rate versus computation time that you need to trade off. And ultimately, the certain fundamental parameters like max depth, that is the depth of a tree, do also affect the regularization or the overfitting. If you have a tree with a very big depth, uh, then you may get very impressive results in terms of the training data. But in terms of the test data, then there will be a bit of a reduction in terms of the predictability, because your model has been trained in terms of the surrounding noise in the training set. So we'll come to the most famous algorithm in terms of gradient boosting, which is called Higgs-Boost or extreme gradient boosting. That was a part of a project by this Chinese American gentleman called Tianqi Chen. And it became famous when he used it in the Higgs-Boson challenge, which came on Kaggle. And the Higgs-Boson challenge, we've all heard of the Higgs-Boson particle or the God particle. And it was this challenge involved a huge number of records. The data set was like absolutely massive. And the advantage with the XGBoost algorithm, especially from passionate data science, challenge participants, is that XGBoost has simply been one of the favorite algorithms in the last 4 or 5 years as far as uh, contest winners are concerned. In fact, in 2015, there were some 25 contests, out of which 17 contests were won by people who used XGBoost. I think that was probably the time when there were more classical machine learning contests on Kaggle than the ones that you see today, where there is a healthy mix of deep learning contests as well. And the advantage with XGBoost is that it's available in multiple languages: Python, R, Julia, Scala, Java. I myself used it in R, where it works very well with something called the Carrot package in R, which is traditionally used to bolster models, tune them better, and so on. It works very well there, and obviously works well in Python. And today's code demo is actually going to be in Python. It's extremely fast. XGBoost. It uses sparse matrices, and it also uses the cores of your laptop better. So there is a block structure. You can parallelly learn and update weights and values, and use multiple cores of your system. And it allows for L1 as well as L2 regularization. In fact, XGBoost allows for regularization at multiple levels. So there is a parameter called eta, which is obviously your learning rate. Then there is gamma, which is a parameter which dictates as to how conservative your algorithm can be. So the higher your gamma, the more conservative your algorithm is. So beyond a certain level, it will not allow the tree to split if there is not a difference being made to the error at that split, a substantial difference being made. So you have not just the traditional learning rate or eta, you also have this unusual parameter called gamma, and you have L1 and L2 regularization. So there are parameters called reg lambda and reg alpha, which you will see when I show you the code. And you can handle weighted data as well in XGBoost. Now, in the last couple of years especially, there has been a sort of cousin of XGBoost, which is also almost equally good. And by almost, I mean it's like all right up there, with a little bit of hair split between this model and XGBoost. And the advantage of this is that it's extremely fast. That's why it's called light GBM, light as in lightning fast. And you can run it even on very large data sets, and it runs in the wink of an eye, literally. I'll try and see if I can show you that on a large data set today. It literally runs in the wink of an eye, whereas you can actually go to sleep sometimes when you run some of these algorithms on large data sets, sometimes on small data sets as well, depending on how heavy the features are. So it uses gradient based one side sampling. So it's much faster than the histograms based split, which is used by XGBoost. and the pre-sort, which the traditional GBM uses. So Gauss keeps all the instances in the dataset with large gradients and randomly samples the instances with small gradients. So compulsorily the large gradient instances are selected and the small gradient instances are then randomly sampled, so that then the overall data processing becomes much faster. It doesn't have to sift through the entire data set and figure out what it's going to do, or look at a histogram based split where you are actually dealing with the small gradient splits first and then gradually working your way up to the large. It's similar to XGBoost, and it also, like another algorithm which we're going to see soon called CatBoost, it can handle categorical features internally. You don't need to do too much of label encoding and one-hot encoding. In this, it can handle them pretty well. So this is the leaf-wise growth structure that it follows, which is very similar to XGBoost. So if you see in the diagram at the bottom of this particular slide, you first have the tree being split into two nodes. So then it takes the node where the purity is higher, and it tries to again split that, and then it again tries to split that. So if you see the second one, it's taking the first one on the left and it's trying to split that. Then it's taking the one on the right, which was split which had higher purity in the second split, and it tries to split that, and so on and so forth. So it's a leaf-wise growth. We finally come to this algorithm called CatBoost, which is developed by the Russian company Yandex. And CatBoost is very convenient when it comes to handling lots of categorical features. So if you have lots of categorical features in your data, CatBoost works very well. So there are a lot of classification problems, data sets, wherein we actually don't do certain operations on the data because we'd rather have the data as continuous instead of categorical, because ultimately we have to label encode everything and change everything into a continuous continuous form. So in that sense, CatBoost allows for a very easy process. It kind of automatically does a sort of its own version of one-hot encoding, and where the number of features or number of levels is less than equal to the one-hot max size, pre-specified hyperparameter, which is an integer. And for the remaining categorical columns where unique levels which are more than one-hot max size, it uses its own internal method of efficiently encoding, a mean encoding method, which is similar to label encoding, but far more efficient when it comes to handling regularization. So that's what CatBoost does, and it's again blazingly fast. So when it comes to running the algorithms, whether it's LightGBM or CatBoost, you can run them in a jiffy. So before we come to the next slide, I just like to talk a little bit on something which is not here but very close to my heart, and I will show it when it comes to the code demo part of it. Now, the advantage of using these ensembled models, especially of the gradient boosting variety, is that all of them are very eminently explainable. By that I mean there are feature importances available of these algorithms which are part of the model objects themselves, which you can easily use to identify which features are important and possibly even make your overall algorithm a little more judicious in terms of the final choice of features, so that the important variables get priority, and therefore if you're working on the algorithm for a business or for any other specific real life purpose, the ultimate action is taken only on those important features, and your model predictability also possibly can improve by just slicing off the important features. So there are multiple schools or multiple methods of getting the feature importances, and this you will see when I show you the code demo. XGBoost has got 3 ways of calculating feature importance. LightGBM has 2 ways of calculating feature importance. So some years back, there was a gentleman called Robert Shapley who developed something called Shapley additive explanations. which is a very game theory way of calculating feature importance, and it includes the intuition of all the different ways of calculating feature importance statistically and combines them. And it also gives you record wise predictions if you want. So for example, if you are a loan prediction company, you can actually show your manager as to why a particular loan applicant should not get by giving a specific analysis for that particular record by using the SHAP algorithm. And it's very easy to install. Pip install SHAP will work. The only catch with SHAP that I must warn everybody on the webinar about is that SHAP is computationally very expensive. So if you have a large data set, unless you have a good performance enhancing system to access in the form of cloud or high speed computing, you may not get the SHAP code to work. But today's code demo, part of it at least, will be on small data set. So I'll actually show you how SHAP works vis-a-vis the traditional feature importance for the algorithm. So this finishes the presentation. I have just one more slide, and I think I'll just come to it now and then move on to the code demo. So boosting is the best off-the-shelf classifier, as we saw, and you can, in the case of adaptive boosting, get rules of thumb and convert them into absolutely brilliant prediction rules. Right? It reduces bias, obviously, which your random forest was not able to do. And these are explainable models with feature importances available, and as well as drivers of importance. Extremely fast to use on big data sets also. They are prone to overfitting and computationally expensive on the flip side of things. So if there are any questions till now, I'd like to take them before I move to the code demo.
Audience, any questions if you have? Once into coding, he may not be able to return to presentation very fast.
No, I can do that. That's not a problem, but I'd like them to sort of ask me any questions if they want. I'm okay with that.
None coming as of now. You can go ahead.
Okay. All right. So I'll take you through this data set on HR prediction. I picked it up from some online course, and then later on found out that it was also in Kaggle. So the advantage of this data set was that the entire data set was available in terms of the ground truth label. So that is why I took it, so that it will be easy for me to show you in terms of how the algorithm gets developed. I'll also take you through two data sets which are actually solved in terms of live contests. One was a live contest I participated in last week and got pretty okay results. And the other was an old Kaggle problem which I used for a recent retail showcase which we did in CellStrat, wherein we used boosting models to actually build demand forecasting prediction algorithms. So this is the data set. It had certain number of features. I added my own features by categorizing certain continuous features and building some features of my own. Right. So this basically whether the employee will stay or not stay kind of a situation as far as the HR is concerned. So this is the entire feature engineering, comparing the features with the predicted the ground truth label. Look at correlation in an alternate way just to see if there's any correlation which is unduly severe that I might need. Boosting algorithms, by the way, are immune to correlation. Yeah, you can run your boosting algorithms even when you take highly correlated variables because it will not affect. The only thing is that when you take out feature importances from those kind of models that you build, those feature importances can be very deceptive because a feature might come out as very important, but you realize that there's another feature to which it's very closely correlated. That's not very unimportant either. So in terms of the model itself, Unlike your logistic regression and support vector machines and so on, your boosting algorithms or ensembled model algorithms are immune to correlation. And there's another thing that I always do in terms of looking at the skewness and kurtosis. So again, this data set doesn't have too many outliers. As you can see, there are just a couple of variables where the kurtosis is more than 3. So it's good to go in that sense. And then I prepare the x and the y variable. And then I, I I first predict my vanilla Adaboost. Yeah. So before I predict my vanilla Adaboost, what is the base learner behind an Adaboost? Right. The base learner behind an Adaboost is a decision stump. So I'm just showing you how a decision stump itself predicts. So a decision stump on its own gives you an accuracy of 81.68 and a raw KUC, that is the receiver operating characteristic area under the curve score of 0.55 or something. We then use a vanilla Adaboost, that is a normal default Adaboost, and basically, so I'm just trying to, I'll just try and show you what are the parameters. Just give me a second while I quickly run this.
I posted the CellStrat YouTube channel link, so you can check it in 2 to 3 days time for the webinars recording.
So we've run the code. Now let's just look at the parameters that are there in a default or vanilla Adaboost classifier. So the number of it uses say 50 trees or 50 n estimators is similar to random forest. The learning rate, default learning rate is 1.0, and the algorithm that it uses is called SAMME.R. So you can read a little bit more when you actually go here. It will tell you about what SAME and the earlier algorithm was called SAME, and now it's called SAME.R. So SAME stands for simple additive multiple. I'll probably get back to you guys on the exact meaning of that. And SAME.R is a more improved version of that, which actually converges faster. So nowadays everybody uses SAME.R. So when we try to fit the Adaboost using this decision tree, one stump decision tree as my base estimator, you get you get 86% and accuracy and 65% raw KUC. We can also try the brute force algorithms, right? So this is just a brute forcing that I've tried here. I'm not going to run it in the interest of time. Yeah, so this is the kind of time it took to run a brute force on Adaboost, wherein I try to build maximum combination of features, whether the split should be in terms of Gini or entropy, whether it should be the best possible split or a random split, whether I should use the traditional SAME or the SAME.R algorithm, the number of trees and the learning rate and so on. So after all of that, I got a certain value, and I adapted those parameters to my existing model. So when I adapted it to the test set, I didn't get a very great result. Whereas the beauty of Adaboost is that it tunes very easily, like I told you in the presentation. So even in the absence of a brute forcing algorithm, you can get a brilliant result. So what I did is I simply changed the original default algorithm that I used. I added 20 trees, and I changed the learning rate from 1.0 to 1.1. Okay, and I got a much better result on the test set. So I got 87% accuracy almost, and raw KUC which almost touched 70%. This is the best raw KUC I got across all the algorithms in this particular data set. Okay, this is a very sort of Kaggle contest, simple kind of a data set. So there is a chance, but in real life, obviously, you may not get features which stand out more versus other features to that extent. But you can get a raw KUC which is better in an Adaboost. There is a lot of similarity between features, and so in those kind of cases, you really don't have any weak learners coming to the table per se, because they're all strong learners relatively to each other. But in this case, there were weak learners, which is why Adaboost did well with a little bit of tuning without even the brute force. The next algorithm I will show you is the GBM. So again, it's the same data set. I've just kept the notebooks separate, but the initial part till the data prep, creation of the X and Y and everything is the same. And in this case, I just took some online code in terms of creating a user-defined function to calculate feature importance using the GBM. Yeah, and you can also source the feature importance using the model object itself, which you get after running the model. But this UDF helped me present the feature importances in the form of a graph, which looks better. So your vanilla GBM is basically 100 trees, max depth of 3. Now, the max depth of 3 is one of the beauties of a GBM. Okay, so like your vanilla random forest is unrestricted max depth, which is why it overfits phenomenally, right? So the vanilla GBM is a very good model where it's 100 trees, a low learning rate, and a very less max depth. So this is something that even if you are careless enough, you know that your max depth is still 3, so you by default will not end up overfitting. And I'll show you how very quickly. Uh, then we look at how this predicts, and then we get the parameters of these. So there are a couple of approaches to parameter tuning when it comes to GBM. One is the learning rate itself. So I think somewhere between 0.05 to 0.2, as long as the number of trees is between 50 to 80 or so, is all right. But the moment you have higher number of trees, then you need to work on lower learning rates. Uh, uh, these are a couple of philosophical things that I personally believe in terms of min sample split and min samples leaf. A lot of the times people take the default min sample split as 2 and the default min samples leaf as 1. Those will lead to very, very highly overfitted trees, and they will also lead to very, very misrepresented model importances. And I will show you that in the case of XGBoost especially. So you must always try and take min sample split and leaf. My personal favorite as a statistician would be to take min sample split as 30 and min sample leaf as 10. So you're always splitting on a data set of 30, not less than that. So max depth can be 3, and typical subsample will always be 0.8 when it comes to any of these models. Even your call sample by tree, which is the number of features that you take, will typically be 70 to 80%. Yeah. So I have done the grid searching. I obviously wanted a better ROC score and not just chase accuracy, but I didn't use accuracy inside my grid search because you don't basically get accuracy as a default parameter inside grid search. There is a way of creating your own ROC or own log loss inside grid search by using this called a facility called make scorer, but that doesn't always give you the same result on the brute force algorithm as the eventual one. So when you fit the model, that is model.fit train set and then model.predict test set, which is why I just went for accuracy. So first I uh, train for the number of trees. Then once you get the number of trees, then you slowly try and see visually represent the results of this to see which is the best number of trees. Yeah, so this number of trees was coming out to be 50. and I looked at the best parameters of my brute force algorithm, and this is a visual representation of that 50 itself, yeah, in terms of test set accuracy. And then I try to, take 50 and predict it on the test set. And then, as you can see, all the other parameters are very low. And then one by one, I tuned all the other parameters. I tuned the learning rate, and then after that, I took that learning rate along with the number of trees, and then in different stages, I tuned the max depth, the min sample split, the min sample sleeve, and eventually the max features. So it gave me a certain value. So tuning is as much of an art as a science, and there are cases when you may not even want to use brute forcing, like how I showed you in the case of the Adaboost, and you may get pretty decent results. So this was my sort of best possible model after all the brute forcing, and then I tried to move beyond the brute forcing and see if I can get something better. So I just moved a little bit beyond brute forcing, and I got something which was similar but slightly better. And maybe if I had played a little bit more with it, I might have even got something better. So these are the sharp values. These are the traditional feature importances in this particular graph. Okay, so you have monthly income, which is getting the highest importance, then overtime, which is the second importance, and total working years, the third importance, and so on. But when it comes to SHAP, you have a completely different way of getting feature importances. You have overtime, which is number one, monthly income number two, and job role, which is number three. So these are nothing but the mean sharp values or the average impact on the model output or magnitude. So this is basically the change in the model value or the model loss when that particular feature is not there. So in this case, the model is using logobots units. Yeah. So the number of units that will be absent when that feature is not there is what is represented in the sharp value. So this particular graph shows that if overtime is not there in my model gets affected to this huge extent versus, let's say, all the other features. So automatically I know overtime is actually my strongest classifier in this case. So this is basically a density plot. Yeah. So a different way of looking at the same model output, but here you're looking at each customer. So each customer, in each of these rows, each customer has a dot, and the X position is basically the impact of the feature on the model's prediction for that particular customer. And the color of this particular dot represents the value of the feature for that customer. So there are some dots that you see which will not fit on this particular line because they're all coinciding. So if you see in total working years at this particular value, you have multiple records for whom total working years has this particular importance. Yes, or similarly years at company, multiple records which will coincide together. And you will have red on the left and blue on the right as well. Yeah. Or red on the right and blue on the left as well. So traditionally, the left hand side is more of reds or negative importance, and right is more of the blues or positive importance. But in this case, you will see there are certain reds, so or certain blues. So for this particular sequence of customers, this particular variable is actually important. Yeah. So these are some variations of SHAP values. I'll quickly show you in XGBoost how the SHAP actually affects. So this is the XGBoost for the same data set. Yeah. So XGBoost not very dissimilar set of parameters. Yeah. So in the case of XGBoost, just a couple of things I wanted to share in terms of data preparation. XGBoost typically takes something called D matrix, whether it's R or it's Python. You have to basically convert the data itself into a matrix, especially if your ground truth label is in the form of a numeric value, right? But if your ground truth label is in the form of text data, then you need not even do the matrix part, at least in Python. This has been my experience in a recent challenge that I solved. So I didn't convert it into matrix, but traditionally XGBoost data is always converted into matrix. So you're not dealing with data frames in terms of your X train, Y train, X test, Y test. You're dealing with matrices. So in terms of the kind of features or parameters you're dealing with, hyperparameters you're dealing with, you have the minimum child weight. Then you had gamma, like I told you, which is the conservativeness or the boldness of that particular prediction you want to make. You have the subsample, which is your bag fraction. You have the call sample by tree, which is nothing but the number of features that you're taking in that particular percentage of features you're taking in each round. Then you obviously have the max depth, the number of trees, and the learning rate. So I put all of this into a brute forcer, and I took randomized search rather than grid search because I wanted to save time. And yeah, so it randomly selected some 25 hits, and yeah, the best set of hyperparameters is here, and then I basically took those to build a tree. And now actually I wanted to focus more into, so I got a 62% raw KUC and 86% accuracy score, not too great, but I wanted to focus in XGBoost a little bit on the feature importances very quickly. So there are three feature importances in XGBoost. You have weight, then you have cover, and you have gain. Now the default importance that an XGBoost uses is nothing but the weight. But this is very risky importance to use in certain cases, because the weight thing takes just simply takes the number of splits that that particular variable causes across the trees. So what it does is that if let's say I have uh, uh, let's say I have let's say I have a feature, and it's splitting the first tree twice, the second tree let's say once, and the third tree let's say thrice. So it causes 6 splits across my 3 trees, which my model has let's say only 3 trees, right? Now the importance of this particular feature is 6 divided by the total number of splits made by all the classifiers across all the trees, by all the features across all the trees. So if there are 30, then the importance for this will be 6 by 30 across, let's say, my 3 features or 4 features, whatever. Now, the problem here is that sometimes these splits can occur when the data size is very, very small. Like I said, the default in many of these cases, your min sample split, that is the minimum number of samples required at a node level to make a split, is 2 by default. The min samples leaf, that is the minimum sample at a leaf or a termination node, is just 1. So unless you actually increase or bolster those particular parameters by default and ensure they're maintained at a robust level, your feature importance by this weight may be very, very misleading. As a good data scientist, you're just running it, and you're new to, let's say, sklearn and Python, and you don't know that these options exist, and you get this feature importance, and you're like, wow, and then you know pandas, and you can make a data frame and make a graph out of it, and you feel great, and you show it to your boss. But then you get a totally different set of feature importances when you look at it by the other. So this is the weight one. Now, if we look at it by cover, so cover is nothing but taking all of this and weighting it to the data size. So the amount of data that is split, the number of observations that are split by these splits made by the variables, actually give the weightage when it comes to cover, as opposed to just the amount of splits that that particular variable makes across. So my personal favorite when it comes to splitting is always cover. So again, if you look at this, the importances will look very, very different. In the interest of time, I'm just running through this. And the third importance here in XGBoost is gain, which is the relative contribution of the feature to the model when you take each feature's contribution for each tree in the model. So the simple rule of thumb here is the higher value means this particular feature is that much more important when it comes to generating a prediction. So I would always take cover or even gain when it comes to looking at feature importance by XGBoost. And if I was advising a business, I would certainly not look at weight. Yeah. So then obviously you also have sharp values in XGBoost. We saw over time in the other one also in gradient boosting. You'll see the same here, and then there you have the density plots as well. So yeah, this is it. And then you also have light GBM and cat boost. So when it comes to light GBM and cat boost, I might just use. Vishal, have you got time? Hello, Vishal.
So we have about 5-7 minutes.
Okay, so then I'll just take another 1 minute on the code demo. I won't run anything.
Sure,
So
go ahead.
so I wanted to actually run this in front of you guys. So this is a data set with 1,000,000 records, and the training data itself is 1,000,000 records. And I split the training data into something like a 80-20. So I had some 800 odd training records, 800,000 training records. And believe me, when the light GBM was running on this data set, it was running at an amazing speed. I mean, I'm sorry about overshooting in terms of time, but so this is basically a regression problem wherein you're trying to basically predict store-wise sales for a retail chain, and you have transaction data on which you're doing it. So you're merging store data and transaction data and creating transaction data for 1,000,000 records along with the store level information for each of those transactions as well. So these are the hyperparameters that you deal with in a light GBM. You have learning rate, number of trees, number of leaves, which is 31 is the default there, number of child samples, the number of data, minimum data in one leaf. So it has these variables have different names in different boosting models depending on who's authored them. Then you have max depth, min child weight, and you have call sample by tree, which is also there in XGBoost. And you have two levels of regularization, reg alpha and reg lambda. In XGBoost, your reg alpha is 0 and reg lambda is 1, and your in light GBM both have a default value of 0. One of them is L1 and one of them is your L2 regularization, and this is a very important hyperparameter which is used in XGBoost, light GBM, cat boost, which is your early stopping rounds, because these models are extremely greedy in nature, so there will be a huge tendency to overfit. So these are the checks and balances that you have in place. And believe me, this was 1,000,000 records, but it ran in the wink of an eye. And I have in this data set, I have also tried to save the training times. If you look at random forest, I took it used to take minutes, like 3 minutes, 4 minutes, 8 minutes sometimes to just run certain iterations. But this ran in the wink of an eye. So light GBM is super fast. And this is a challenge I did last week using boosting algorithms. This is a multi-class classification. So the winner got something like 88.5. I got something called like 86.1. And so there are 4 classes to predict. And this is a website called Hacker Earth. So this was a live challenge where they were giving some prize money and all that. And I basically didn't have much time because there was something else I was working on. But I used, I didn't even do much feature engineering because of the lack of time. I simply did some ADA and for the sake of my own integrity, and I just moved after that. So if you look at the algorithms I used, I worked almost for 4 hours to build a random forest, and I got a score of 83 at the end of it. So I got a certain score in terms of my train test data, and I realized that everything is overfitting by 10%. So within half an hour, I got a GBM value after a little bit of tuning using the brute force algorithms. I got a GBM value of my model which was like 95 or 96% on my best set of features. So I selected the one which was like 96, my best set of features. This was the one, yeah. And I made a prediction on the test set using this one, yeah. And this is the prediction. So this gave me a score of 86.06. I tried matching it using light GBM 2 or 3 times and also XGBoost once. So this is the XGBoost one wherein I have not converted the data set into a matrix. Yeah. So it's multi-class. So you use multi-class soft prob. Okay. Otherwise, you normally use binary, or if it's regression, you use reg error. So please go through the websites of each of these algorithms. Apart from GBM, all of them have a separate website because they're all standalone packages. XGBoost recently has got a version on scikit-learn. Yeah. So I
So
try
there
my
is a
best to match it.
question.
Yeah, sure. Yeah, please
Yeah.
ask.
So question is, in multi-class classification, how do you decide whether to proceed with one versus one or one versus all methodology? I understand that one versus one can tackle class imbalance problem while being computationally expensive as
Yeah,
opposed to
yeah, yeah.
one versus all. Apart from these, what are some other factors to be considered in practical scenarios?
Okay, wonderful. So yeah, so thank you for asking that question first of all. That makes a lot of sense. So you can use one when it comes to imbalance. First of all, you can use methods like SMOT, or you can use SMOG and SMOG. And when it comes to regression problems, where you see that there is a certain kind of imbalance between the features, key features themselves, yeah, or the proportions within the key features which are predicting the outcome value, yeah. But in this particular problem, I didn't use a one versus rest classifier because there was not much imbalance between the four classes. There was not one particular class which was standing out like huge in terms of the ground truth, or neither was there a class which was standing out to be too less. I typically took a call in this case, a judgment call, and said, let me go ahead with without using a one versus rest classifier. But otherwise, yes, one versus rest classifier is a good to use thing when you're handling imbalance. So this is the ground truth. If you see, it's not there's nothing which is, so you have 30 which is the highest and 16 which is the lowest. So you don't have anything which is in the single digits, and you don't have anything which is above, which is like 50% and above. So these are fairly balanced classes. Does that answer your question?
Sure.
Okay, so yeah, that's it from me. Apologies for overshooting time a little bit, and yeah, thank you to Vishal for organizing this and CellStrat for giving me this opportunity. If you
No,
want
just
to get in touch with me, sorry.
yeah, go ahead and share your details, please.
Yeah, sure, sure. So this is me on LinkedIn. I'm Natarajan Lalgudi, and that's my email ID, natarajanlalgudi.ai@gmail.com. So uh, in a week, 10 days time, I'll be uploading these codes on my data profile. In the meantime, if you have any questions, you can write to me on LinkedIn or on my email ID. So this is just showing you how I look, or at least how I used to look a few years ago. But yeah, it's not too different. So yeah, so this is me on LinkedIn, and yeah, this is my email ID. So natarajanlalgudi.ai@gmail.com. And yeah, you can write in to me. And boosting is a topic I'm very passionate about. If this time at disposal, I'll look into it and respond. If I can't respond immediately, I'll let you know by when, and I'll definitely give you a reply. So thank you very much for listening and being a great audience, and thank you once again. Self.
Thank you, Natarajan, and thank you, audience, for joining in. Uh, I hope Natarajan will be giving some more webinars in future, and look forward to see you in further webinars. We almost have next week, probably we have 2 or 3 webinars, and in March we are trying to get almost every day there will be a webinar except weekends. So look forward to see you again. Right? Have a good night to all in India and good day to some others from across the world.